Hello everyone and welcome back to Explore Engineering. In today's video, we'll learn a program where we'll see how to generate a sinusoidal sequence using MATLAB. A sinusoidal sequence is one of the most fundamental signals in digital signal processing and is widely used in communication, audio processing, and signal analysis. Using MATLAB, we can easily define the signal parameters such as amplitude, frequency, and sampling interval and visualize the waveform. Here in this video, we'll see two programs, one to generate the continuous time signal, that is continuous time sinusoidal signal, and another program for generating discrete time sinusoidal sequence. So let us start. Here you can see the definition of the sinusoidal sequence, where the definition states a sinusoidal sequence is a discrete time signal whose amplitude varies according to the sine function and it is periodic in nature. Now, since the signal repeats after a fixed interval, it is called as a periodic sequence. And this repeating nature makes sinusoidal signal ideal for representing waves such as sound signals, communication signals, and alternating current waveforms. Next comes the mathematical expression. So here the sinusoidal sequence, it is mathematically represented as y of n is equal to sine of 2 pi fn, where y of n is equal to amplitude of the sinusoidal sequence, n is the discrete time index, f is the normalized frequency, that is in cycles per sample, and pi is the mathematical constant, that is equal to or approximately equal to 3.1416. Now here the value of f, it determines how quickly the waveform oscillates. A higher frequency produces more cycles within the same number of samples, while a lower frequency produces fewer cycles. Here we can see an example plot where the sinusoidal sequence is generated for frequency f is equal to 0.1. Now here the graph is displayed using a stem plot here, okay, which is the standard method of representing the discrete time signals. Now from the graph, we can see that the signal is starting here at 0, okay, and it increases to a positive peak, then it decreases back to 0, it reaches a negative peak, again it returns to 0, and the same pattern repeats. So this repeating waveform demonstrates the periodic nature of the sinusoidal sequence. Next comes the characteristics, that is the key characteristics. Here first is the periodic sequence. The waveform repeats after a fixed number of samples, which is called as the period. Next is the amplitude, where the amplitude always lies between -1 less than or equal to y of n less than or equal to 1. Okay, that is, it may vary between -1 and +1. Then comes the frequency. So here the frequency, it controls how fast the waveform oscillates. For small value of f, there will be a slow oscillation. For large value of f, there will be a fast oscillation. Then comes the discrete time signal. So here the signal exists only at integer values of n. Then you have representation. Because it is a discrete signal, it is normally displayed using a stem plot instead of a continuous signal, okay, or the continuous curve. So these characteristics are for this example plot, okay. Then next comes the important properties, where first property is the periodicity, where the sequence is periodic if f is equal to k by n, where k and n are the integers and k and n are co-prime. So here the sequence repeats after capital N samples. This is n, no, after capital N. Then next comes the period. So the fundamental period, it is the smallest number of samples after which the waveform repeats itself. Then you have amplitude, where the maximum value of the sequence here, it is what? It is +1. Okay, and minimum value is what? It is -1. Therefore, the waveform always remains within these limits. Then you have even or odd property. So y of n, it is an odd sequence, that is y of minus n, it will be minus of y of n. So this property indicates the symmetry about the origin. Then here we have a example, MATLAB code example, where it shows that it creates a discrete time index. Okay, so here it is creating a discrete time index. Then it defines, that is minus 22 plus 20. Okay, this one. Then next it defines the frequency value, that is f is equal to 0.1. Then it will generate the sinusoidal sequence using the sine function. Okay, that is sine of 2 pi fn. Then comes here, that is displaying the output using the stem function. Okay, this one, stem n comma y filled, then grid on. Now you have to label the x-axis and the y-axis. So here x label n and y label is y of n. Here you can see this is the x label n and this is the y label y of n. So the output graph matches the example plot which is shown here. Okay, here this MATLAB code is for this particular example, and even these characteristics are for this one. Okay, that is the general characteristics. Now comes the applications. So here the DSP, that is a digital signal processing, it is used for analyzing the digital signals. Then audio and speech processing for representing the sound waves. Then communication systems for transmitting and receiving the information. Signal modulation and demodulation in wireless communication. Filter design and testing for evaluating the digital filters. Now, because many real-world signals can be represented as combinations of sine waves, the sinusoidal sequence forms the foundation of many DSP techniques. So here you can see a note here, that is the value of f must satisfy 0 less than or less than f less than 0.5. That is f frequency, it should be greater than 0 and it should be less than 0.5. Now, this condition, it is related to the Nyquist criterion, which helps preventing the aliasing when representing or sampling discrete time signals. So here the summary for this is that here the sinusoidal sequence, it is given by or represented by the mathematical equation y of n is equal to sine of 2 pi fn, which is a fundamental discrete time signal whose amplitude varies between -1 and +1, and its oscillation depends on the frequency f, and it repeats after a fixed number of samples. And because of its periodic nature and wide range of applications, it is one of the most important signals studied in the digital signal processing. Okay, next here we have the continuous sinusoidal sequence versus the discrete sinusoidal sequence. So here you can see this is the continuous time sinusoidal signal, where the mathematical equation for this is x of t is equal to a sine 2 pi ft plus phi, where a is amplitude, f is frequency in hertz, t is time in seconds, and phi is the phase angle in radians. And here you can see this is the discrete waveform, and here this discrete time sinusoidal sequence, it is represented by x of n is equal to a sine omega n plus phi. So a is amplitude, omega is angular frequency in radian per sample, then n is the sample index, that is the integer, it will be an integer, and phi is the phase angle in radians. Okay, so here the key features for the continuous time sinusoidal signal are, it is defined for every instant of time and infinite number of points in any interval. There will be infinite number of points in any interval, and it is described using the using time t. Okay, and here it is plotted using the plot, that is plot command. Then you have applications that is used in analog signal analysis. Okay, and here the key features of the discrete time sinusoidal sequence are, it is defined only at discrete instants of time. Okay, then it is finite or countable it has finite or countable number of samples, and it is described using the sample index n. So it is plotted using what? It is plotted using the stem function, and it is used in digital signal processing. So here you can see the features, and you can see the differences between the continuous time sinusoidal signal and the discrete time sinusoidal signal. Okay. Now comes the program. So here this program is to generate the continuous time sinusoidal signal. So here you can see the program here. These three commands will be common as usual, and next here we have written t is equal to 0 is colon 0.001 colon and 5. So here it will create a time vector from 0 to 5 seconds with an interval of 0.001 second. Then here you have frequency of sine wave, that is f is equal to 1 hertz. Okay. Then comes the generation of the sine wave by using the mathematical function. So that is y is equal to sine of 2 pi ft. Next we have to plot the sine wave. So we will use plot t comma y comma g line width and 1.5. So this will plot the sine wave in green. Here we have written G, no? So it will plot the sine wave in green. You can change the color. You can make it R blue, or you can make it B for blue, like that. Then comes the Y label and the X label. Okay, X label is what? X label is for X axis, that is time in seconds, and Y label is for Y axis, that is amplitude. And the title, okay, the title here we have to give the title for the graph, that is we are giving it as sine wave. Next here for display we are using it as grid on, which will display the grid lines. Okay, you can see these lines now, these square boxes, okay, light gray. So that is that appears by using this grid on function or the command. So it displays the grid lines for better visualization. Now here you can see this is for the discrete time sinusoidal sequence. Okay, so here again these three commands are common, that is CLC, it will clear the command window, and clear all, it will removes all the variables stored in the MATLAB memory, and then close all. Okay, it will close all the previously opened figure windows. Then here our actual program starts here. So first we have to define the parameters. A is equal to 1. It will set the amplitude of the sinusoidal sequence. Then you have omega is equal to 0.2 into pi, which specifies the angular frequency in radians per sample. Then we'll take phi is equal to 0. It means there is no shift. Okay, that is there is no phase shift here. Then you have n is equal to 0 is to not is to colon 40, which creates the discrete time index from what? From 0 to 40. Okay, here 0 to 40. Then we have to generate the sinusoidal sequence by using the formula x is equal to a sine omega n plus phi, which will compute the sinusoidal sequence. Next you have to plot the sequence. We'll use the stem function here, stem of n comma x. Okay, so here it will define the it will display the discrete time signal. Then we have the x label and y label. X label for horizontal x-axis, that is the sample index n. Then y label for the vertical axis as the signal amplitude. Then you have title sinusoidal sequence, which will add to the graph title here, sinusoidal sequence. Next you have grid on, which will display the grid lines, and you have axis, okay, that is 0, 40, minus 1, 1, which will sets the axis limits to match the figure. Now here you can see because we are generating two samples, okay, that is two signals. One is for continuous time signal and one is for sinusoidal signal. So here you can see the difference or the comparison of the two MATLAB programs which I have seen. Fine. So here these are the key differences, that is we have consider the feature as type of signal. Here it is continuous time signal and here it is discrete time signal. Then independent variable, that is the time t, and here it is sample index. Okay. Next you have frequency used. Then it is here it is used in hertz, and here angular frequency we are using, that is in radian per sample. Next you have plot function. After that the graph appearance. Okay. Then comes the applications. So here You can see the difference. So both the programs here will generate the sinusoidal signals only, but the representation is different. Program 1 is used for continuous time signal analysis, while program 2 is used for discrete time signal analysis in the DSP. So understanding both the programs helps us to distinguish between the analog and the digital signal representations and their practical applications. Now we'll see the execution of the program in MATLAB. So I will copy the program from here. You can type the program. Here already I have pasted the program. Once again I'll do it. Always you have to write or type the program in editor window. Okay. Now next you have to save it. Now I'll save it as sinusoidal continuous. Okay. So here always the files are stored in .m extension. So save. Okay. Okay, we have to change its name. I will keep it as it is. Now I will save it and I will run it. See, here you are getting this figure window. Here you can see you have generated the sine wave, that is a sinusoidal wave, continuous sinusoidal wave, or the sine wave whose amplitude is ranging from -1 to +1. Okay, and you can see the x-axis, that is we have taken it as time here, and y-axis we have taken it as amplitude, and the title of this is sine wave. Okay, this is for the first program. Now we'll see for the discrete sinusoidal wave. So for discrete sinusoidal wave, this is the program. I will copy here only. Okay, I'll save it, run it. See. So this is for the discrete sinusoidal sequence. You can see here the index. Okay, that is the sample index. It is varying from 0 to 40. Fine. And here you can see the title of the sinusoidal sequence. So this is nothing but the program about sinusoidal sequence, where we are generating the continuous sinusoidal signal and the discrete sinusoidal sequence. So here you have seen like these two programs will demonstrate how to generate and visualize the sinusoidal sequence, and by changing the amplitude and frequency or sampling interval we can observe how the waveform changes also. That also we can do, and this experiment helps us to understand the characteristics of the discrete time sinusoidal signal as well as the continuous time sinusoidal signal, which forms the basis for many DSP applications. Thank you.